Professor Goldner. We haven't had a biophysicist in a while as a guest in our colloquium series, so I'm very pleased to welcome her. I'm excited that she accepted our invitation. In particular, since she's a fellow spectroscopist, her current area of research is looking at biomolecules in a complex environment, and she's looking at them one at a time, if you may say so, right? So you're going to hear about that in a second, but let me tell you that she graduated with a PhD from University of California at Santa Barbara in '91. And then she spent, I guess, 9 years almost, 17 years at NIST. Yes, that's correct. And then she moved here in 2008. Here by here, I mean in New England in 2008. And she's been at UMass Amherst since then. So before she starts, I want to give her a tiny token of our appreciation for driving that long stretch of highway from the New Hampshire border that we all know and love.
88 miles on each highway. Exactly.
Yes.
88 miles on each one.
Yes, and no billboards and no restrooms. So that's why we're especially grateful. And this is your laser.
Yes. Okay, great.
Let me turn it on for you. Yeah.
Is it working?
Yeah, it's working. That's fine.
Okay, good.
Thank you very much.
And the laser thing is done? Yes, okay. Okay, so I'd like to start this talk with this picture. I don't know if any of you have ever been to the West Coast during the Great Monarch Migration, but if you're in the right place at the right time, the trees are covered with these things. In fact, I remember someone was telling me recently that they were watching them and they were going to see the migration, and they came to an eucalyptus forest somewhere, and they were looking and they didn't see any butterflies, and then they realized that the trees were the butterflies. They were just completely covered with layers and layers of them. And it's really quite an amazing phenomenon, and you might wonder how these tiny little insects actually fly thousands and thousands of miles every year. And if you wanted to know something like that, if you want to learn something about this mass of butterflies, how do you learn something about butterflies, right? How do you learn something about the behavior of these butterflies? Well, the first thing that some people try to do is this, right? Where you take your butterfly and you stick a pin through it. And that allows you to get some information about structure and how the thing is put together. But it doesn't really tell you about what you want to know, which is why are they migrating, how are they migrating, how does this happen, right? What are the dynamics here, what are the mechanisms here? So this is we've all seen these in museums there. I remember as a kid going to museums and seeing whole collections of various bugs and butterflies with pins through them. And it's a good first attempt. A better attempt is something that was published in PNAS a few years ago. I love this paper, it was just lovely, where somebody decided they were going to try to understand the mechanism of what it is that drives a butterfly to migrate. So they tethered the butterfly in such a way that it was stuck in this jar, but it was free to fly and free to rotate. And dang if this thing didn't always head directly south. And even if you reached your hand in and turned it into a different direction, right, it would almost, just within a few seconds, it would find its way south again. And the result of this paper was to figure out that, in fact, butterflies navigate by the sun. They're pretty clever about it. You can really mess them up by moving them from time zone to time zone, because they have an understanding of what time the sun is where in the sky. So that was a really neat trick involving tethered butterflies. Now, if you want to know more about what drives butterflies, what their mating behaviors are, why they're doing this migration, or what they do once they get there, then you might do something like make a habitat, right? Where I don't know if any of you have been to the butterfly habitat in Deerfield, Massachusetts, but they tend to be around here and there, and if you have little kids, you almost certainly have found one at some point. These big buildings that are designed to be butterfly habitat, and you walk in and the butterflies land on your arms. They do what butterflies do, and they usually have an incubation room somewhere where they're making caterpillars and this sort of thing, and making more butterflies. So with molecules, we have a similar situation. We have lots of different ways to look at individual molecules, and we can do things like pin them to a surface. This is a single, I believe this is a phage that has been exploded. This is DNA. This is one enormous DNA molecule you're looking at here. that's just exploded out of this virus viral capsid. You can also tether molecules to a surface. You can actually, in solution now, make some sort of a biomolecular glue and stick your molecule on the surface and let it sit there and flap in the breeze while you study it. And then you can also do what I'm going to talk about today, which is put it in a sort of a habitat, which is a very tiny little attoliter droplet, attoliter volume droplet that's about 100 nanometers across, where there's surface all around, but it's a very different sort of surface than you get here. These glass surfaces tend to be heterogeneous. You're very near a very unbiological boundary. And here you have a droplet, you can tune the surface, you can do different things with the surface of it. It's a much more homogeneous surface. And the molecule is free to diffuse and rotate inside of that volume without sticking to the walls. So that's what I'm going to talk about today, is what happens when you put molecules in droplets. Before I start, because I often don't get to the last slide, I want to make sure I give credit where credit is due. Of course, all the work done in here, nearly all of it, is done by students and postdocs who worked with me over the years. My current graduate student, Shima Raman Suresh, is the main person working on the RNA project. She's looking for a job now, and she's absolutely my best student. She does fantastic work. Ben Gamari, Kieran Ramos, Peker, Malas, and Nina Zafrush all contributed to this. The undergrads at UMass are awesome, and there's a bunch of them here. James, especially Alvar Milder. Louis Perot did the MD simulations you're going to see. Ryan Pahela and Samson Del Pula and Trevor DeMille are all working on pH and droplets, and they're currently in the group. The last two are currently in the group. Okay, so I hope you'll stop me with questions. I'm going to talk about a few different things today. I may not finish this last one depending on how far we get. By the way, this goes until 4:30? 4:20? We can give 4:20 minutes for questions. Okay. Okay, good. So I'm going to talk a little bit about the motivation, why we measure single molecules and why we might want to use droplets. I gave you a little bit of that just now, I'll give you a little more. Then I'm going to talk about the technique that I'm most interested in, that we use most around my lab. A lot of different techniques, but this is the one I'll discuss today, which is fluorescence resonance energy transfer, which is a way of measuring distances and even angles between two spots in a molecule and between two different molecules. I'll talk about what happens to fret when you put the molecule in droplets, and then I'll talk about what is actually, to me right now, one of the more interesting parts of this story, if I get to it, the inside story, what's going on inside that attoliter volume droplet, because that turns out to be quite a fascinating story in and of itself. So this is not the usual thing. Microfluidic devices typically use micron or 10 micron droplets. They're femtoliters, they're nanoliters. They're not attoliters. This is really quite a lot smaller than your typical droplets you find in devices. So all sorts of new, I think there's some new physics going on actually, but there are new chemistry certainly. Okay, so why measure single molecules? So if you have as you saw, butterflies, and you want to know something about the butterflies, if you have a group of people running the Boston Marathon, you want to know something about how people run the marathon, you don't really care about the average velocity of the flock of people who are running the marathon. And the average velocity of the butterflies is interesting, but it's not that interesting. You really want to know about the behavior, how the guy at the front of the race got there, for example, in the marathon. You want to know about what he did or she did to train, right? What are they doing? How did they get where they are? So you get more information about the ensemble by doing single molecule measurements. You're actually measuring the bits of the ensemble instead of just getting average numbers. If you have a heterogeneous ensemble, you can distinguish it from one that's homogeneous. You're not making any assumptions about Gaussian distributions. You're measuring the distribution. If you hold on to a single molecule and watch it over time, you can get kinetics, equilibrium kinetics, and dynamics, how the molecule bends or folds or twists or does whatever it does over time. There are a lot of processes in nature that are single molecule. If a virus infects a cell, it's taking a single piece of DNA or RNA and injecting it into a cell. It's one molecule at a time, through a single molecular pore. It's a one molecule at a time type of event. From my point of view, I really like this one. So it turns out our droplets are getting to be about the sort of size that you can simulate in an MD simulation. And the time scales between MD simulations and single molecule measurements are slowly converging too. Right now, you can reasonably, on a GPU in my own lab, we can simulate a microsecond worth of MD simulation, and our measurements sort of start at the microsecond time scale. So we're beginning to meet in the middle. And so if I'm talking about a molecule in a droplet, I'm talking about something that looks an awful lot like a molecule in a water droplet that we use in the simulation, and the time scales are slowly beginning to converge. About 10 years, I think they'll be quite well overlapped. And finally, there are practical considerations. If you do single molecule measurements, if you do microfluidic measurements with tiny droplets, you're talking about less sample, less waste. There are lots of good reasons why you might want to get smaller and scale up these sorts of measurements I'm going to talk about today to many droplets. Okay, so why droplets? So first of all, when you attach a molecule to a surface, just like when you attach that butterfly, right, you're perturbing it for sure. There are certain behaviors you'll be able to measure and others that are going to be perturbed. And I can show you lots of examples of places where we put molecules on surfaces and we see what looks like heterogeneous behavior, and in the end it turned out it was a heterogeneous surface and not the molecule at all. So surfaces are a pain. They're particularly a pain if you're looking at certain proteins, and especially something that's all the rage right now, these disordered proteins. Disordered proteins tend to be inactive on surfaces. Things that undergo large changes tend to denature on surfaces. So proteins don't like being near surfaces, and this encapsulating things in a small droplet is a way to keep them away from the surface. Again, very efficient use of small samples, I said that already. And finally, the one that down the line is really the most exciting to me is the possibility that you can look at out-of-equilibrium events. You can do chemical reactions in these Attoliter test tubes. So you can imagine, component A, component B, they come together, they mix, one molecule here, one molecule there, and you can watch a reaction happen in real time. So to look at out-of-equilibrium dynamics, this is very exciting. And we've demonstrated that it can be done, but this is still way too tedious a method to use. So one of the things we're doing currently in my lab is working on trying to make devices to do many droplets in parallel. But today I'm going to talk about just single droplets and what goes on in a single droplet. All right. Thanks. Oh, and finally, something that we actually hadn't anticipated, but I'm going to show you some measurements today done on molecules and droplets that are freely diffusing in oil. They're not being tethered to a surface, they're not being optically trapped, they're just diffusing around. And this has a certain advantage over watching molecules diffuse around because the droplets diffuse slower, so you can watch them for longer. And I'll show you what I mean by that in a moment. Okay, where do I talk about what the droplet is? I'm going to draw something that I should have put in right away that I didn't. So when I talk about droplets, I'm talking about sort of 100 nanometer droplets surrounded by perfluorinated liquid. And the perfluorinated liquid is liquid Teflon. Nothing sticks to it. They're very biologically inert. They hold enormous amounts of CO2 or oxygen. I think it's something like 60 or 70% oxygen by volume. So you can actually breathe these things. There was a famous picture on the cover of Science News when I was a kid. It got me interested in science. It's one of those things that stuck in my mind for all these years, of a rat whose tail was tied to a weight at the bottom of a giant beaker. And the beaker was filled with some fluid, and the rat was clearly, it's a photograph, but the rat was clearly alive and swimming upward. And the caption read, "Rat after 45 minutes in perfluorinated fluid." It had been breathing this fluid. There was a science fiction movie, I think, that came out of that, actually, a few years later.
The Abyss.
Yeah? I don't remember the name of it. Do you remember what it was?
The Abyss.
The Abyss, that was it. Yes, that was it. At any rate, so they're very biologically inert fluids, and that's what I mean when I'm talking about a droplet. Okay, so I'll show some pictures of that, be more specific about it later. So the motivation here, my own personal motivation, is that there are certain systems that I would like to look at that I just gave up looking at on surfaces because of the heterogeneity problem. One of them are these RNA-protein interactions, where here I'm looking for a very subtle change in the structure of a piece of RNA when it binds to a protein. Very hard. I tried doing this on a surface, and I won't even go into all the problems we had, but eventually I hope to be able to do this in droplets. We're looking at it now just in solution without the droplets and getting somewhere, but I think the droplet technique will help us a lot. If you want to look at structural fluctuations and flexibility of DNA, surfaces perturb these sorts of dynamics. And so to be able to do that in a droplet would be a very nice thing. As I said before, there are some very big proteins. This is a serpin. It's a fantastic molecule. This was in collaboration with Ann Gershenson a long time ago, and I hope to get back to this one day. This is a molecule that is basically a mouse trap. It's sitting there in this high energy state, and it waits till a trypsin, this is the serpin. It waits till a trypsin comes along. A trypsin is a protease. Comes along and clips a bond up in this loop somewhere. I think exactly where it is. It's up here somewhere, I think. At any rate, as a result of that, an enormous amount of energy is released, and this domain just gets pulled right down through the middle and out the other side, and it moves like several nanometers. It's an enormous motion. You can't look at these anywhere near a surface. They just denature on the surface, or they're inactive on the surface. And finally, we had some crazy ideas to look at nucleation inside of very small droplets, where you could imagine working, if you wanted to grow crystals, people have been growing crystals inside of droplets for some time now, but you could imagine working with just a few molecules such that your density is higher than what you need to nucleate a crystal, but the number is smaller than what you need for a critical nuclei. So what happens then? You know, could you possibly catch intermediate states forming and falling apart? So that was our crazy idea that we haven't started to pursue yet, but it's just something to think about. All right, I'm going to talk about looking at some of the molecules using fluorophores, and most physicists here don't know what I mean by a fluorophore. Who's ever played with fluorophores or dyes before? How many people know what this is? Okay, how many people have no idea what I'm talking about? All right, good. So everything, almost everything absorbs light to some amount, to some extent. And if it absorbs light, it's almost certainly going to spit out a few photons in return. But this isn't like a hydrogen atom. A hydrogen atom, you excite it at a certain wavelength, you get the same wavelength back, or pretty much. Dye molecules are big, fluffy molecules, or bigger molecules that typically live in solution. And what will happen is you can excite it from some ground state to some excited state with a photon, and then there are various ways for it to get back down to the ground state. But if something is a good dye or a good fluorophore, overwhelmingly what it's going to do is it's going to kick back another photon. And that photon is not at the same color as the one you put in. It's always redshifted by quite a lot. That's called the Stokes shift. And it has to do with the fact that the solvent reorients itself. It's the energy of the whole world that you're interested in. So when you kick this molecule up into the excited state, all of a sudden the water molecules around it find themselves in a high energy state. They have to reorganize. By the time that happens, the energy is lower and you end up with a photon that comes out that's a lower energy. So you get this big Stokes shift. Practically speaking, it can be 20, 30, 50 nanometers. Maybe even more sometimes. It's quite large. And it makes it easy to separate the excitation light from the emission light, from the fluorescence light with filters. It's how fluorescence microscopy works and how dyes work in general, or fluorescent dyes. There are other things that can happen, and these other things that happen limit the fidelity of your experiment. For example, the lifetime of this excited state is about a nanosecond, which you would think means, oh, I can get about 1 billion photons per second out of this thing. I can cycle it at about 1 billion photons per second. But in fact, there's always some obnoxious triplet state here, some state that is forbidden. You can't go from here to there with a photon or from here to there with a photon. But if you have a collision or you have triplet oxygen around, you can end up in this triplet state. And then it takes you tens of microseconds to get out, or 1 to 10 microseconds to get out. And that effectively limits, that gives you a saturation for this cycling to the excited state, which practically is maybe 10 to the 6 or 7 photons per second, of which you can collect 1 to 10%. 10% on a really good day. So now you're down to 100,000 photons to 1 million photons per second. And if you run the molecule that hot, you end up spending a lot of time in this triplet state, and this triplet state is reactive, and you can end up photobleaching, and then you have no dye molecule at all, and your experiment is over. So practically speaking, you can collect about 10 to the 4 photons per second. That's your signal. And then you might get, if you're lucky, a few minutes out of your measurement. Okay, so that's what I mean by a dye molecule. We're going to use these guys as little nanoscopic voyagers, what's the fantastic voyagers, right? Not many students know that reference anymore, but old movie. These guys basically are reporting back on the environment around them. They're little nanoscopic molecules that, by the polarization of the light that comes out, by the spectrum of the light that comes out, by the intensity of the light, by the lifetime of the excited state, by all these different sorts of properties of the photon, I can tell something about what's going on around that molecule. And the particular technique that I'm going to exploit the most in this talk is called fluorescence resonance energy transfer, which actually requires 2 dyes. So, what's going on here? Right. I want to do it in that order. I want to do it in this order. Okay. So in fluorescence resonance energy transfer, I have 2 dyes. Okay, I will do it in this order. So for example, I have a donor dye here and an acceptor dye here. By that I mean this is going to be a bluer dye and that's going to be a redder dye. And in fluorescence resonance energy transfer, what's going to happen is I'm going to excite this higher energy dye. And if it's close enough to this one, then I'm going to get a near-field dipole-dipole interaction that's going to transfer the energy from my donor over to my acceptor. And I'll see light from both of them coming out. Or I'll see a shortened fluorescent lifetime for this one because it's got a quenching channel. It's got something else to take its energy away, which shortens the lifetime of this one. So there are lots of different ways to do this. Okay, and the molecule I'm going to use today is very simple. We're going to stick with this is a physics talk, we're going to stick with the simplest possible molecule. This is just a 16, where I like working with RNA, but before the measurement scientists didn't even remember, I spent 17 years at NIST, so I really want to understand what I'm measuring. And there was enormous debate in the literature about exactly what you're measuring when you put dyes on the end of a piece of RNA like this. So we're putting our dyes, they're cyanine dyes on the end of the RNA, and I have a structure here that I know, I can calculate it, I can model it, I can even model the dyes on the end of it, as I'll show you in a moment. So I should be able to calculate from first principles how much energy transfer I should get between those two dyes, and then I should be able to go to measure it. And so the way this works again is that if you have a donor dye whose emission spectra overlaps the absorbance of a spectra of an acceptor dye, then you'll get this energy transfer. But it's not a radiative transfer. You're not getting, this guy's not kicking out a photon and that guy's not catching it. Completely wrong picture. If you remember, those of you who are graduate students or undergraduates from E&M, when you calculate the fields of a dipole, there's the propagating field, right, which is the one on R field, but there's also a one on R squared and a one on R cubed component, which you ignore because it doesn't propagate. But that's exactly the field that's really strong in the vicinity of the dipole. So if you think of these dye molecules as little dipole antennas, little radiating dipoles, then that's the field we're talking about. That evanescent field, that near field, you excite this one, and you end up seeing fluorescence from that one because they're transferring energy between their near fields, right? And so it's going to be a 1 on R6 dependence on the distance. So the probability of energy transfer looks something like this, where R0 is a scale factor that's typically about 5 nanometers. It can be calculated from first principles depending on things like the index of refraction of the medium, and this is a very important and often, almost always neglected polarization factor. It's the polarization term, it's the orientation term in the dipole-dipole interaction. And it basically tells you that if you have two dipole antennas that are lined up, they're going to talk to each other. And if they're like this, they're not going to talk to each other. Okay? In almost all work done with fret, it's assumed that the dyes are freely rotating, and so you can take an average value for kappa squared, and its average value averaged over all angles is 2/3. And in almost all work done out there, kappa squared is taken to be 2/3, and R0 is taken to be a constant. And by the way, this is the quantum yield of the donor, and this is the spectral overlap. So these are all things you can measure or calculate. And in principle, you can predict exactly what you should get for this energy transfer. Okay, so again, the emission of one dye overlaps the absorbance of the other. That's when you're going to get some fret. This is the 1 on R6 dependence, the probability of energy transfer as a function of distance if you have a kappa squared of 2/3, if you have a freely rotating dyes. Notice that the importance of R0 is that E is 1/2 when R equals R0, right? And it's just 1/2, so this is R0 right here in this dye. Typically around 5 nanometers, 50 angstroms. Okay. The way you measure fret is by looking at how much light is coming out of the acceptor and you compare it to how much total light is coming out from both. That's one way of measuring it. So you're looking at how much light is coming out from this dye relative to how much is coming out here or to both. And there is a precise way to measure this. I'm not going to talk about that today. We can measure this number exactly, but it requires doing a bunch of corrections that I really don't want to talk about because they're gory details. What I'm going to talk about today instead is the closely related proximity ratio, which is just the number of photons coming out of the acceptor channel. You have a microscope with the donor, and you're looking separately at the donor and the acceptor light, filtering out using filters. And you just look at the number of photons in the acceptor channel over the number of photons total. And that gives you a measure of fret. You have a lot of acceptor light. If this thing is approaching 1, then you have 100% energy transfer. If it's 0, you have no energy transfer. Right? So, this is our molecule, and this is an MD simulation done by Louis Parot and also Peker Melas had a hand in this. And the first thing you notice is that, so notice that this is your duplex RNA, and notice that the dyes, the base pairs are all base stacked. A lot of the energy that keeps RNA together is not just hydrogen bonds, it's the fact that you get these nice stacked pairs of nucleic acids. you win a lot energy-wise by having these guys stack up like pancakes. Turns out the dyes want to stack like that too. And in fact, you very rarely see them do anything else but stack if they're cyanine dyes. Occasionally this one will go on a trip. Psi5 almost always sticks. Psi3 occasionally comes off. In fact, at the very beginning of this, you may have noticed it started off unstacked. We always start them unstacked, and they always just find their way back pretty quickly. So there's no way those things are freely rotating. Okay. So now what I'm going to do is talk about Fred in droplets. What happens when you put RNA in droplets? So we have this system that we love because we can predict what we're going to get. We know what we should get from it. And the question is, what do we get in solution? Does it match up with what we expect to see? And what do we get when we put the same molecule in droplets? I should say I've also done the same thing on surfaces, and the results were such a disaster we never published them because they were all over the map. And since then there have been other studies showing the same thing, so there's not much point in it. But you get really different behavior on surfaces. You get heterogeneities from this very simple system that should have had just a single Fred value. And the values are different again. So I won't show that data. So this is the droplet. Again, just to remind you now, we have a droplet now. It's typically, okay, let's call it 270 nanometers in diameter. That was the average size for one set of measurements. It's about 135 nanometers radius. Your RNA molecule is about 5 nanometers, so this isn't quite to scale here, but you get the idea, it's smaller. Sometimes we use surfactants, sometimes we don't. But just notice how small this thing is. So when I say a water droplet, I'm really talking about a buffered water droplet. So you always put buffer in to try to hold the pH constant. And typically when you're using tris, we have about 20 millimolar tris, so that's about 120,000 molecules of tris buffer inside of this little sphere. Okay? We're using about 200 millimolar sodium chloride always, so there's quite a lot of salt. There's about 1.2 million salt molecules, and about 340 million water molecules, and then one RNA. Okay? And these are small, like I say, 135 nanometers is about a 10 attoliter volume. Okay? And that's just a picture of one you'll see over, this is a picture we took many years ago of a larger size droplet, so you can see it's about a micron in diameter. And what we're going to do is we're going to optically trap these droplets. Okay, so what that is, without going into detail, yeah?
I was just asking a question.
Oh, please do, I'm sorry. I should have
A technical question?
Yeah.
In forming the droplets, is that just pressure? I mean...
Okay, we have a couple different ways we do it now. In the past, we always used ultrasonication. Now we're extruding them. We can't use ultrasonication if we want to do proteins because it just rips them apart. But we can extrude, I think. So we've just recently started the same extruder you used to make liposomes with, you can use to make droplets, using almost exactly the same technique. So we just discovered that recently, although we haven't quite figured out, there's a lot about that we haven't figured out yet, because liposomes tend to track the size of the pores, and the droplets seem to like to be a certain size no matter what size pore you use in your extruder, which is a bit puzzling. And we may not quite be right about that yet, we're still trying to pin that down. But it does work, it makes very lovely emulsions. So what we do is, one of the nice things about water droplets and perfluorinates, perfluorinated oils are one of the few oils, they're not in oil, they're liquid. They're one of the few liquids in which water is immiscible, really immiscible, that have a lower index of refraction than water. And that means that you can optically trap the water droplet. So an optical trap is just a dielectric trap, is all it is. You take an IR laser beam and you focus it way down, you have this enormous field gradient, and you'll find that dielectric particles get pulled into a field gradient. So I don't want to talk about that today, about why, but I want to just say that what we can do is we can have a microscope that has in it an optical trap overlapped with a focused detection volume. So it's a confocal microscope, you have a focused volume. You're not imaging, you're just making a tightly focused laser spot and you're collecting light from that tightly focused laser spot. Okay? So we have our droplet in an optical trap, and in the droplet is a molecule, and we can collect in two different channels the light coming out, two different color channels, the light coming out from that molecule.
Can I clarify? You
Yeah.
have like buffer inside the
Yep.
liposome and some other solution outside.
Yep, it's not a liposome, right, because exactly, because it's water inside and perfluorinated liquid outside. FC77 or FC40 are our two favorites by 3M. And FC40 is used pretty widely in the microfluidics industry. So, yeah. And sometimes there's a surfactant, sometimes there isn't. You can make these with or without surfactant, and these are not stable emulsions. They're kinetically trapped. They're just, the droplets are far enough apart that it takes them long enough to coalesce that we don't have to worry about it. We usually let them settle for a half hour before we use them, and then they're fine. And this is the instrument, right? So you have a detection volume here with your tightly focused laser spot, and there are two lasers, your IR trapping laser and your excitation laser to excite the donor dye, for example. And then the light is collected back through here. This is what's called a dichroic mirror. It passes longer wavelengths and reflects shorter ones. So the excitation light is reflected, but the emitted fluorescence is collected back through it. And then it's divided again into two channels, the donor light and the acceptor light. And yes, you do get a little crosstalk, but for the most part, you can separate them. And then we just have our own homemade system for collecting. We actually time every photon that comes in. Depending on which system we're using, we're either doing nanosecond or picosecond timing. So every photon that comes in, we give it a timestamp. We collect the timestamps. All right. And this is the typical sort of data that we got years ago. So this was the first data we got back when I was working at NIST. And we immediately had a problem. First of all, it was very hard to get this data, and we never understood why. Things would photo bleach very quickly, but these were typical sorts of things that we would get. So at this time here, the red trace is your acceptor molecule, and the green trace is your donor dye. Okay, acceptor dye, donor dye on that piece of RNA. At about half a second here, we turn on the laser light, and immediately you see the acceptor light comes up, so you know you have FRET. So you have energy transfer between this green and the red, and ignore the black symbols for the moment. You immediately see you have energy transfer. At some point, around 2.5 seconds or so, the acceptor molecule photobleaches, it dies. And you know that's what's happened because you see immediately this green light comes up, and there's no structural transitions here. This is just one molecule, it has one structure. It shouldn't be doing anything funny. So this dies, that comes up, and then sometime later the donor molecule photobleaches, and now you have background. And suffice it to say that from a picture like this, I get my background from here, I get crosstalk between channels from there, I get FRET from here. I can accurately tell you what the probability, what the efficiency of energy transfer is. And I get a histogram. I'm actually using a different technique here, using the donor-only light, and I'm getting this sort of a histogram where the FRET efficiency is very, very high. Now, we had predicted a number around 0.6 or so for this, and we were really surprised to see this. And we did it again later, and we got another big number, around 0.8, sometimes higher, sometimes a little lower, but it was never around 0.6, not in droplets. And so a couple of years ago, we got smart and we said, forget the optical trap, let's just let these guys diffuse around, let's get a pile of data. Now we can look at millions and millions of these droplets as they diffuse through our laser beam. Okay? No optical trap. It's the same way we do the molecules. You can do molecules in solution this way too, and it's commonly done, single molecule sensitive detection of molecules where you just let them diffuse through your laser beam and you collect the light as they diffuse through. The difference is here you get about 100 microseconds of diffusion time, and here you get about 10 milliseconds of diffusion time, because the droplets diffuse so much slower. Same setup otherwise, no trap laser. And immediately, well, okay, so this is what the data look like. I'm plotting the donor data upside down on top, so you can see it more easily. And this is the acceptor data on the bottom here. And you can see pretty much for the RNA in solution, almost every time you get a blip in the donor channel, you get a blip in the acceptor channel. Sometimes you don't because the acceptor is photo-bleached. And if you blow up this little section right here, this is about 30 seconds worth of data across the bottom here. If you blow up just this little blackened in portion there, you see that you pretty much, if I'm binning this in, I think it's 5 millisecond bins here. It doesn't say, but I think these are 5 millisecond bins. You see that you're really only getting 1 point. Basically in 5 milliseconds, the freely diffusing molecules go on. It takes about 100 microseconds on average to cross the beam. So it gets in, it gets out, and you get a few photons. You get maybe 20 photons out of one channel, and maybe 10 out of the other, or something like that. And you get 20, 30, 40 photons out total. For the droplets, now SC77 has about the same viscosity as water. So here the whole effect is that the droplet size is bigger, so it's moving slower. Okay, and it goes with the diffusivity scales with the radius. So if it's 100 times bigger, it's moving 100 times slower. So here, we have much larger peaks. And on top of that, they're not just a single point in time. If I blow this same little region, little half-second region up, I see that these guys all have width to them. So now I'm getting hundreds of photons per crossing, at least. Okay? And an FC40, which has about 4 times the viscosity of water, I get even more photons out. So now I start histogramming up. I ask, well, what values do I get for frets? So what I'm going to do here is I'm going to look at all the photons that are, for all the bins, say, for which I have above 10 photons or 20 photons or 30 photons total. And I'm going to take the proximity ratio, number in the acceptor channel over number in the acceptor plus number in the donor, and I'm going to histogram it up, right? So it's all taken in the same microscope. What I get in solution, sort of what we always expect it to get, it's around here somewhere. You get a big broad peak, it's actually heterogeneous, but that has to do, that's something we cannot model, but it's widely attributed to the fact that Cy5 isomerizes, Cy-dyes isomerize, so you tend to get more than one state of the dye, and I can talk more about that later, but anyway, this is your RNA in solution. You get a pretty broad peak, and it looks sort of homogeneous, but really you need 2 beta functions to fit it, and I'm using beta functions, not Gaussians, because the beta function is the moral equivalent of a Gaussian on a bounded interval. Remember, this proximity ratio can only go between 0 and 1, right? So that means when I get off to the sides here, I'm going to get something that is asymmetric. So I'm not fitting the Gaussians, I'm fitting the betas. And I can't fit this quite to 1. It's always a little homogeneous, heterogeneous. But when I go into RNA and droplets, lo and behold, remember that high fret value you saw before that we never understood? There it is. And it's really heterogeneous looking. And in FC77, it seemed even worse, which never made any sense to us. But it was similar peaks, but bigger splitting, narrower here. And notice that the average number of photons per bin is much higher here than here, which means that, which gives you the, which might be the reason why you're resolving these 2 peaks, for example. You get better statistics, you get narrower peaks just from that. Okay? And this had us really stymied for some time. And then when we tried a lot of different things. And Peker Malas, I have to give him credit for this, he's a student who figured this out. He said, what about pH? So we started looking at RNA in solution at pH 5. The Cy-dyes are supposed to be completely insensitive to pH. But the backbone of the RNA starts to protonate below about pH 6 point something. So the behavior of the dyes on the RNA is going to be completely different because the dyes are also charged. You know, the dyes are going to, the electrostatics are going to change, basically. It's not even that they're charged, the electrostatics are going to change. And so the behavior of the dyes is going to change. And so we started seeing these crazy looking high fret peaks. And if I took this data here, these data here, and simply threw out enough photons to get the average number down to the same average number here. So I'm just starting to throw out photons to get the statistics to look the same. It's not perfect, but they're beginning to look similar. Okay? I can't increase this. There's no way to increase that. That's limited by how fast things diffuse. But I can throw photons away, and they're beginning to look similar. So, we're beginning to suspect pH, and I'll tell you, jump to the end really quickly and just tell you, since I may not get there, that we are now measuring the pH in these droplets, and it is indeed quite low. Turns out that if we start throwing in non-ionic surfactant, this is a non-charged surfactant, no charge on this surfactant, it's just perfluorinated polyether with a peg in the middle. It's the same surfactant the entire microfluidics industry uses. We had been throwing in a little, but not enough apparently. When we started throwing in at least 2%, at least 1%, these 2 guys started looking very similar. Again, we have higher resolution here, so we get narrower peaks. But the averages, the center value, especially at this peak, is exactly the same. The bigger peak is always the same. Same thing at 1% surfactant. If we go to 0.1%, we start seeing this funky looking double peak again. And again, if we now go into RNA in solution at pH 6 and we start throwing away, we actually had a better, we just got better data on this data. Turned student taking the data, so the threshold was way up. We just got nicer. I said there was no way to up this, but in fact, better alignment. We got more photons out here, so we didn't have to throw away as many there. And these guys really are a little bit different. This one's always a little more heterogeneous than that, at least at low pH. So that's still a mystery. Why is there some heterogeneity? So I'm going to conclude this part of the talk, and then I'll talk a little bit more about the droplets themselves. So the conclusions here are that just the fact that you're confining molecules in droplets, which is a very easy sample prep, by the way, just the fact that you're doing that at all gives you way better signal to noise in your single molecule diffusion measurements. So we're going to pretty much start doing all of our single molecule measurements this way from now on, just confining things in droplets. We get a better dynamic range, and we get better signal to noise. All around win-win. We seem to be able to control the pH as long as we put in enough of this surfactant. I do not understand why a non-ionic surfactant does this. And if anyone has any ideas about that, let's talk. I will tell you why I think there's a pH effect in a moment, I hope. That's what I just said. So there is a pH effect. I'm about to tell you why I think there's a pH effect. And finally, the distinct heterogeneity is something we don't understand. Now, in case, let's see, I have 5 more minutes. Let's see how far I can get here. Okay, so just a reminder again, this is our molecule, our droplet rather, or the molecule inside. The first question I always get asked is it sticking to the surface? Does the funny effects that we're seeing have something to do with the surface? Yes, it has something to do with the surface, but it's not sticking at the surface. When you have something stuck at the surface, you get an image that looks like that. This is a liposome with dye in the membrane. Okay, a small liposome with dye in the membrane. Well, this one's pretty big. It's like 18 microns across. That one's smaller. It's only about 3 microns, 4 microns across. But that's a droplet. And it's a big droplet so that we can image it. But if I take a cut through it, I mean, the dye is distributed inside in about the way you expect it to be. So the dye is not sticking to the surface. Is it interacting with the surface? I would say absolutely. How? I don't know exactly, but I do know that just if you have a sphere and you have something diffusing around in a sphere, remember most of the volume of the sphere is out in the outer shell, right? The volume grows pretty fast as you move out in R. So if you just model Brownian motion inside a sphere, there's an old paper by Duxer where he does this very simply with reflecting boundaries. We're trying to do the same thing now, but we're trying to mess with the boundary conditions a little bit.
I think it's usually, at least for when we do electron microscopy, we have to be careful because some molecules like to go to the surface.
Yes.
Not everybody.
Of course, of course.
So
absolutely.
I can see.
We've done this with, we've done rotational, I can tell you that we have done rotational polarization anisotropy lifetime measurements on RNA, on DNA, on various proteins, and we've never seen any of them stick. So the stuff we've been interested in anyway doesn't stick. But if you ask yourself about the linear translational diffusion, and this is taken with a huge grain of salt because we're using a model that is probably almost certainly not correct. It's a model for a freely diffusing Brownian diffuser in a cylindrical Gaussian diffusion volume. But if you take those intensity traces I showed you before with the fluctuating intensity, and you take the correlation function of one of those, that's called fluorescence correlation spectroscopy, and it tells you something about the dwell time of a molecule in the detection volume. And if you look at pH 6, you get a correlation function that looks like that, and you can tweeze out a single diffusion time of about 366 microseconds. So it actually, for various reasons, goes up. It's about 150 microseconds. It doubles from pH 7.8 to pH 6, roughly doubles. So anyway, you get about 366 microseconds. If you look at the droplet, you expect to see 2 diffusivities. You expect to see the diffusivity of the molecule in the droplet and the diffusivity of the droplet. And indeed, you do see 2. You can't fit with fewer than 2. This is FC77, this is FC40. But in both cases, the shorter one, which you would naively expect would be limited to this as a maximum, assuming the droplet is smaller than or about the size of the volume, it's always bigger. So whether that's because we're just using the wrong model, which is completely possible, or whether it's because there's some not sticking, but some hydrodynamics going on at the boundary that tends to keep the molecule there a little longer maybe than it should be, than it would be if it were a reflecting boundary. We don't know yet. We're actually, I have an undergraduate working on modeling that on the GPU and a graduate student trying to do a brute force. So we're working on it, trying to see if we can model this data. Okay, and finally, I mentioned, I won't talk about this because I do want to talk about, we have been measuring the pH using pH sensing dyes, and this is just some preliminary data showing as a function of the surfactant concentration, the pH starts down at about 5.5 or maybe even lower with no surfactant, and then comes up to about where it ought to be. We started at 7.8. And these are preliminary. I'm actually be doing the calibration for that as we speak. But something like that. The one thing I wanted to get at is why. And this is where I think things are really interesting. So I'm going to spend the last minute talking about why droplets are acidic. Okay, so this steps right into a huge morass. I was really astonished when I started looking into the literature on what goes on at the surface of water. There have been recent papers in PNAS entitled things like, "The surface of water is acidic," and then a paper in response to it titled, "The surface of water is basic," in some other major journal. So there's an enormous discussion about what's going on at the surface and exactly and a lot of it centers on what exactly is meant by the surface. One thing is clear to me. There's a series of experiments by James Beattie some years ago where he did the opposite sort of emulsion, regular emulsion. He took oil droplets and put them in water, right? And made an emulsion of oil droplets in water, the inverse of what we're doing. And he measured, it's easier that way to measure the pH of the continuous phase, right? The water phase in that case. You can just take your pH meter and pop it right in there. And he measured the pH of the continuous phase and noticed that it was dropping the smaller he made the droplets. He just kept homogenizing and homogenizing, and as the droplets get smaller and smaller, the pH is dropping. And he measured how much sodium hydroxide you had to keep throwing in to keep the pH constant. And from that, he discovered that he needed something like 1 hydroxide ion for every 3 square nanometers of surface, which is a lot. It's about 40,000 negative charges on the droplets we're talking about. And by the way, it's probably similar, it turns out that almost any dielectric particle you put in water, or even air bubbles that you put in water, if you put a voltage across the water and look to see which way they move, what's the charge on the droplet, you almost always find that it's negative. This is called the zeta potential measurement, and the zeta potential measurement tends to be not small. It tends to be something like minus 50 millivolts or minus 100 millivolts. It's big. It's really big, and it's never been known. It even happens if you do this with no salt. If you take everything out of the water and keep things as pure as possible, you always get this negative charge. So the James Beattie and Gray Wheel explanation for this, which is the one I'm buying at the moment, put my money on anyway. It's the only one I found that seems to account for everything in the literature. Because if you do different sorts of surface-sensitive spectroscopies, nonlinear spectroscopies to look at the surface, you usually find positive charges, if anything, at the surface. But that's really only sensitive to the surface, to the surface layer, to the thing that's right where the broken symmetry is, right at the surface. What the Beattie-Gray Wheel explanation goes something like this. It turns out that for a hydroxide ion, hydroxide has the largest dielectric decrement of any ion, arguably. There's a couple of other ions that are also known to go to surfaces that are contestants in this game. But the hydroxide ion has an enormous dielectric decrement. That means that if I take a hydroxide ion and I throw it into water, the dielectric constant of the water drops more for that one per ion than for almost any other ion. That's presumably a result of the fact that the water coordinates very strongly around that hydroxide. And the dipole fluctuations, the van der Waals fluctuations, right, that hold the water together, that make it a solid, good solid in the first place, and that give water the amazing dielectric constant of 80, right? Those fluctuations are suppressed in the vicinity of a hydroxide ion more than they're suppressed in the vicinity of almost any other ion. So that means that the free energy, those molecules aren't free to do their van der Waals thing, they're not free to fluctuate. So the free energy of that sphere around the hydroxide, that drives the free energy up, right? The fact that these things are frozen, that there's some layer immediately around the hydroxide where the water is just frozen, and then there's a layer around that where the fluctuations are suppressed. That raises the free energy of this whole structure. which will tend to drive it to the surface because then you have less of these frustrated ions that can't fluctuate, frustrated waters rather, that can't fluctuate. There's also an entropic argument by Gray-Wheel that I think is largely the same thing, although I haven't quite finished making my way through that one yet. But I think it's going to be the same, similar sort of thing. There's an entropic argument to be made here as well as an energetic argument to be made as to why hydroxide ions get drawn to the surface. But when you consider that at pH 7, you know, the thing that's amazing about this is for this to work, remember I only had about as many buffer ions in there, buffer molecules in there, as I end up with hydroxides on the surface. So they're all ending up at the surface. Water must be hydrolyzed. This must be such a strong, you're almost hydrolyzing, maybe even you're hydrolyzing water at the surface for this to happen. You know, you're really ripping the water apart or pulling it to the surface, pulling the hydroxides to the surface for this to happen. So that's the explanation, but I think still bears some testing. I think it's quite fascinating. It's going to happen anywhere you have a lower dielectric material. This is what makes it relevant also to biology and cell biology. If you have a lower dielectric material left next to water, or a dielectric particle, anything with a lower dielectric constant than water, which is almost everything, this is going to happen. So, and I'll stop there. So I think I have a reason that still bears some more testing for why the pH is modified in these droplets. I don't understand this yet, unless it has something to do, why are especially the low pH histograms, FRET histograms, why are they distinctly heterogeneous? So if there is slower linear diffusion inside of droplets, if there's some sort of a hydrodynamic boundary effect that's slowing down the kinetics, maybe it's also slowing down the molecular kinetics. And one of the reasons that I could be seeing heterogeneities inside of droplets is that at low pH, you're going to start to see more fraying of the ends of the RNA. And under those conditions, the side dyes will intercalate. When they intercalate, they get brighter. So let's say I have two states, a bright intercalated state and a not so bright. And we do see that one state is brighter. They didn't talk about this, but you do see a new bright state that grows in at low pH. So let's say we have a bright intercalated state of the dye and a not bright unintercalated state of the dye. And we have some switching back and forth between them. So if something is slowing down the translational kinetics inside a droplet, maybe it's also slowing down these chemical kinetics, these structural kinetics. But I really have no idea. That's my crazy guess. Okay, we don't know what's going on there. And I think that's pretty much, and this is the other big unanswered question in my mind, is if Beatty is right, how is adding a non-ionic surfactant changing the situation? I don't understand that either. And with that, I will acknowledge my fantastic artists, Anna Gibson and Trevor DeMille. Trevor did this one. Trevor's also a physicist working on the pH project. Louis Perot, again, did the MD simulations. These are undergrads who worked on the project and grads who worked on various aspects of this, and funding has been from a couple different places now. We're now starting to work, and I expect this to be the same for any oil, but compliments of the Petroleum Research Fund, we're going to be doing this in hydrocarbon oils as well.
Earlier missed that one. Did you say the FRET measurements on surface is bad?
Oh, okay, let me qualify that a little bit. There are people who do it a lot better than I do, but back in the early days of FRET, when all of us were using BSA and trying to find ways to get PEG on a surface that was uniform, we tried them all, and all of them had terrible heterogeneous FRET, and all of them had polarization anisotropy, had polarization signatures. In other words, I can show you data, I may even have it with me, of polarization modulation experiments done for molecules attached to surfaces in different ways. And the one that worked best was actually biotinylated. If you're using nucleic acids, the one that worked best was biotinylated BSA. But even there, an awful lot of them were either stuck or very seriously hindered in their motion.
And why do you think so? Why is the data on the surface bad? Is it because
Well, it's a polarization effect, that I can't trust my FRET data because I'm not seeing an average over, when you're looking at a molecule in solution, it's tumbling and you're getting an average over all polarizations. But now say I have a molecule that I'm looking at fret, and my dyes, as they are on nucleic acids, are not stuck down tight, and one of them happens to be pointing right up along the z-axis of the microscope, and the other one happens to be like that, and I've got some hindered motion around that point, I'm not going to see this at all. If this is my acceptor, it's going to look like I've got no fret.
So you
Right.
have perturbations from this?
So we were getting, I'm pretty well convinced that the problem on surfaces was hindered motion or sticking, more hindered motion than sticking actually. And it was a polarization effect that was giving me artificial numbers for fret. It was giving me crazy, heterogeneous looking numbers for fret because of the polarization effects. Combination of the fact that the dyes are stacked and there was hindered motion on the surface. And if you're TJ High and you're doing this and you're using these beautiful pegylated surfaces that he now makes and you've got a long tether on it, maybe you're okay. Maybe you're okay. In fact, we're trying to do that now. We're going back to doing some surface measurements now that there are slightly better techniques for putting things on surfaces. So. Yeah.
So the main kind of diagnostic information you get from this fret is just the distance between the two dyes.
Yeah, so ask me to give another talk. So one of the things we're looking at that's really cool, that came out of all of this and all of this careful modeling, is that it turns out that for dyes on RNA, we are absolutely uniquely sensitive to twists, changes in angle between the ends of the RNA. And so we're looking at this kissing complex now, and we're looking how ROP protein binds it, how a particular protein binds it. And for the longest time, it was thought that ROP must change the bend angle, which would show up as a change in distance between the dyes. But instead, it's a really cool story how we know this, but instead I'm 99 and 44% sure that we're seeing a twist. We're seeing a change in twist upon binding. And the way I know that is there are actually 3 distinct states of this dye, and you can identify them by lifetime. Because the side dyes are their lifetime, their fluorescent lifetime, and their quantum yield is very sensitive to the rigidity of their environment. So a dye that's base stacked is rigid. It has a long lifetime. A dye that's flopping around has a short lifetime. So we can do lifetime measurements, and we can distinguish the changes in the short lifetime due to fret from changes in the long lifetime due to fret. The long lifetime gives us twist, the short lifetime gives us everything combined. But in particular, it should give us distance, and actually should give us distance. And we're not seeing any change in the short lifetime, we're seeing a big change in the long lifetime. So we're seeing twist. It's actually, there are 3 lifetimes, so it's a little more complicated than that.
So when you see these, what you call heterogeneous distributions, so you seem to not like that, but I mean, it doesn't just mean that there might be, why is it clear that there's only one unique configuration?
Okay, so when you're doing ratiometric fret, you're averaging necessarily, because you have to collect a bunch of photons to get that ratio, the Na over Na plus Nd, you need a millisecond, say, to get data. In that millisecond, you're undergoing many, many of these transitions. The lifetime of these different structural states of the dyes is, we can see them transition in our 1 microsecond of Nd simulation. So they're 10 or 100 nanoseconds. They're longer than the lifetime of the dye, which is why you can't use any approximation. You have to do a first principles model, which I didn't talk about, but you have to actually use the irene-gopic method of a first principles model for calculating fret from the Nd simulation. One of the cool things about that, by the way, and I think where this is going down the line is, we're doing calculations now on a GPU, where in a month we can get a microsecond. If I could get that down to an hour, I could start thinking about using my fret data as a constraint on the Nd simulation, which would be really cool. Because we're starting with the Nd simulation and calculating fret from that. And we can even assign different structural states, different lifetimes when we're doing the calculation. So, yeah. Did that answer your question? Okay.
What's stopping you from using larger lipid droplets? Because you have this...
Oh, nothing. So we could do lipid or droplets.
The droplets you...
Okay.
I meant...
Yeah, so our goal in all of this is to be able to do turf. And I have a project, I have a student right now working on that IDVR project in the middle there is to do this full field imaging on many droplets at once. And for that to work, you really want them to be a couple 100 nanometers, 300 nanometers or less.
Okay.
So that's what we're trying for.
So I was thinking if you had a larger...
Yeah, we can use a larger droplet. We used to do this. We used to use micron-sized droplets, and we'd open up our aperture of our... we'd close down the back focal plane aperture and open up the size of the focal volume, and then you could still get the whole droplet in the focal volume.
Right.
Which you can do. You get higher background that way. But if you want to be able to have a field of these and do a lot of them at once. See, the other nice thing about perfluorinates that I should mention is they're really low surface energy fluids, so they wet everything. So we are hoping that by using a glass, it doesn't work with PDMS, but it looks like when we use a glass surface, the water is just not getting near the glass. So we have, and the droplets don't stick, they can be confined. We're going to sort of try to confine them on a surface, but they'll be confined between glass plates, but not sticking to the water won't be adhered to the glass at all. The perfluorinate will be there. So we're hoping we can just make a field of these things and do a lot of single molecule experiments at once instead of doing them, and then do trajectories. Right now we're getting a snapshot as the thing diffuses through. We want to be able to sit there and look at it over time. And if this works, it'll be so much easier than the surface preps that are done now, which are a big pain. I mean, I think it's fair to say that a lot of us who do these sorts of single molecule fret measurements anyway, these fluorescent measurements on a surface, spend most of our time on the surface prep if you're doing it. Most of your time is teaching students how and learning how and improving on the surface prep. But the droplets they're just easy to make.
So your droplet is highly ionic, is that correct?
It's not ionic. They're uncharged.
They have a soft.
But they have this surface layer of charge. So they have
But the inside is a solution.
Inside is solution, but what happens, so the whole droplet should be negative.
Whole droplet is pretty negative, but inside is highly ionic, which you have a lot
Oh yes,
of.
yeah. Inside is, right, so the OHs are on the surface, and that leaves the hydroxyl, what am I looking for, H3Os
Yeah, right.
inside, right?
Have you tried to reduce the ion concentration inside?
Yeah,
I know the RNA won't be happy, but...
we've played with this a little bit. There's a lot to do. We've played with it a little bit. You have to be careful how far down you take the concentration, because there comes a point where you can't make droplets anymore. Because you need some salt in there to be able to, otherwise the surface tension is crazy. You can't form little droplets. If you don't throw salt in, you can't make small droplets.
What about changing the different type of ions?
Yeah, that's something we have. If I had an army of students, you don't know how badly I want to do that.
It's those ions that make the DNA concentrated.
There are so many things that I want to try to do. Yeah.
I see. So you need a certain ionic concentration to make the droplets.
Yeah. It's easier to make droplets if you throw in some salt. It doesn't have to be 200 millimolar, but that's just where we usually work with our DNA, RNA anyway. And a little magnesium.
How homogeneous are your droplets?
How what?
Homogeneous inside, sorry.
Oh, interesting question. So, first we let them settle a little bit to get rid of the big ones. The big ones float to the top and go away. Then what we're left with is, it's always a log normal distribution, at least, actually we haven't checked that yet for the extruded droplets. For the ultrasonicated droplets, we expect it to be a log normal distribution, but as log normal distribution go, it's pretty tight. So we get most of our, something like 95% of our droplets are between, for one measurement, it was something like 80 and 160 nanometers. So that's sort of the spread.
Could that, because in every
In
case
radius.
you actually have a, what you are describing is the surface volume ratio for your
Yeah, right,
ions,
right.
right? So could you force them to one side to see almost like your pH?
We can do better than that. So one of the things that I know we can do, and that I had a student working on, and he unfortunately gave up on it, is you can track these things. And if you can track them, you can measure their Brownian motion, and you can track them while you're doing spectroscopy on it. And so you can,
Let's say it's a big
I can tell you by its Brownian motion how big it is, and then the spectroscopy tells me what the pH is, because I put a pH sensing dye inside. So in principle, I could do this. In practice, again, it comes down to I don't have the hands in the lab to do it. I've been wanting to do that particular experiment for years. And I thought I had a student who was going to do it, but I didn't finish it. Yeah. Sorry.
So you've done intramolecular fret. Have you ever tried any intermolecular fret in problem?
It depends what you're talking about. The kissing complexes are two pieces of RNA that bind together. I have not looked at stuff coming together and falling apart. That is on the list of things to do, but we haven't done that yet. I really wanted to do that with the I was hoping to be able to do it with the raw, but it's a long story, I won't go into it. But yeah, there are things I'd like to be able to do that we haven't done. The only complexes we've looked at are pretty stable. They don't come apart. We're looking for structural changes. And in fact, when they do come apart, we're going to be looking, I hope, sometime very soon at the one of the dimerization initiation sites in HIV, Mol 60, I think it's called. At any rate, the Mol site, the Mol structure, and that falls apart. So we're going to actually tether it. This is an analog. I don't know if you know Panley's experiments on pulling on kissing complexes. People pull these RNA kissing complexes apart and measure the different structural transitions. And the question is what happens in the absence of force or in the force only of the tether between the two. So we were going to try to do the zero force analog of the pulling experiments that Panley has done at Albany.
So I guess where I was getting at, you could either look at, binding interactions of two proteins, but theoretically, if you had enzyme and substrate or something like that, then you might be able to get enzyme kinetics at the single molecule level.
Actually, this was the first, I should have mentioned this, but so single molecules, you can almost argue that the first single molecule measurements were done in I think it was the 60s, by Rotman, who took beta-galactosidase, is that what it's called? It has a substrate that becomes fluorescent. And he took these single enzymes and stuck them in huge droplets and measured the activity of single enzymes by looking at how fast the fluorescence grew in. And he saw, he could count how many enzymes were in a droplet, and he could also look at differences between, in the catalytic rate between enzymes, between single enzymes. So he wasn't seeing a single molecule, he was just seeing the fluorescence grow in. But he was using droplets to isolate individual enzymes. So yeah, there are all sorts of experiments we could think of doing, and the mixing stuff, I mean, I would love to be able to do some sort of mixing to actually see reaction. That's way down. Unless I find a really good microfluidics collaborator who wants to do this, I think I'm going to get scooped on that one because someone else I know is working on it now. So, yeah.
Very early on in one of your slides, you have a picture of the two bubbles.
Yeah, we did that. So we did the first experiment showing you could do that.
Is the background solution has a flow?
Okay, yeah, that picture, which is also on my website, has been a mystery to me for many years. What we had been doing was we've been using two traps and bringing the molecules together with two optical traps, bringing the droplets together with two optical traps. And we did an experiment where we showed you could take chalcofluor dye and calcium and put them together, and you can see it change in tiny droplets. But we were playing with these injectors one day. I made these little tiny femtoliter volume and sub-femtoliter volume injectors, and my postdoc had put two of them in the same scope when we were first trying to do this experiment. And lo and behold, they just no trap, nothing. They just started. All he was doing was translating. There was flow because he was by hand translating the slide, translating so the injectors in that picture were fixed. And the sample was being translated. And he's just doing this and taking video of it, and every droplet is just going boing, boing. And he actually reproduced that a couple times, but it wasn't particularly useful for doing measurements because there was no trap or anything, he was just moving them along. So in the end, we ended up using two traps, but it was a mystery to me why that was happening. I have to think it had to be hydrodynamics, because I just can't think of any other reason why that would have happened. There has to be some hydrodynamic thing going on there with the flow around the tips. Yeah, it's a good movie. Makes the point that you can mix. They mix, unlike a liposome, they mix on contact.
The other thing is, are these droplets, do they have a lifetime or they stay forever?
Oh, these guys stay. In perfluorinated liquids, they stay a long time. You can, if you spend an hour, you will notice that some of them are evaporating. They do very slowly, but the solubility of water in the perfluorinate is part per billion or something like that. It's very small. So it's very slow, but you do, especially if you heat them up in a trap, you can start to see a little bit of evaporation. But it's not a huge, in the lifetime of a measurement, you don't notice it at all.
All right, one more question. Let's thank Lori again.